Hey guys, this is Mr. Riz here. I'm going to help you out with the 2.4, the applications worksheets for the chain rule here. So we got a couple problems that we'll go over kind of together, and then the last problem I'll just give you guys kind of a clue of what you guys should be doing. Make sure you guys can see this here. All right, so the length in millimeters from nose to tip of tail of a Siberian tiger can be estimated using the function where length is equal to 0.25 times W to the 2.6 power, where W is its weight in kilograms. Also, when a tiger is less than 6 months old, its weight in kilograms can be estimated in terms of the age in days by the function the W equals 3 plus 0.21a. Okay. A lot going on there about tigers. All right. At what rate is the length of the tiger increasing with respect to its weight when it weighs 60? Okay. So anytime it says at what rate, let's make sure we got this down here. It says at what rate, that means we're going to take the derivative. We're going to be taking the derivative of the length function with respect to its weight, which it already is. All right, so part A here, what we're going to do here, I'm just going to kind of help you out a little bit, but you'll take the derivative. So L prime would equal, all right, well, actually not 0.25, you'll have to multiply here. So whatever 0.25 times 2.6 is, let's see, that's 0.13 cut in half of like 0.65, that's what it is, not 0.75. So L prime was equal to 0.65 W to the, drop it down a power, 1.6 power. And then what you're going to do here is just plug in 60 for W. So 60 to the 1.6 power times, so you'll get a decimal, but that's the rate it's changing with respect. So that's going to be millimeters per kilogram. All right, next question, part B here. It says, find how long the Siberian tiger is when it is 100 days old. So we're trying to find its length. All right, when it's 100 days old, its age. Well, what we can do is, since length is determined by weight, and weight can be determined by age, we can go ahead and take 100 and plug it in to figure out how many. So its weight would equal 3 plus 0.21 times 100 days. So the weight should be, that's what, 0.21 or 21 plus 3. The weight should be 24, and we'll take that answer and we'll plug it into the length. So the length would equal 0.25 times 24 to the 2 points. So you can go ahead and figure that out. The next question, though, is at what rate is the length? So we're going to find the derivative, but we're going to have to find it with respect to age. So we could have made a length problem that is length is equal to 0.25 times, well, not W to the 2.6 power, but W is 3 plus 0.21 days old. So if we want to find out the rate here, we'll have to take the derivative. And if we take the derivative of this, we got to use the chain rule. So it's going to be, let's see, we already said that's what, like 0.65 of that something to the 1.6 power. Now the derivative of that something is 3 plus 0.21a. We need to make sure we times by the derivative of the inside. The derivative of the inside is just 0.21. So to figure out C here, this is L prime, you're going to have to simplify this equation here and then plug in 100. So that should be the amount of millimeters per day. Pretty interesting if you actually get a number and see how fast that Siberian tiger is growing. All right, so that should help you out with the first problem. Next problem here. All right, suppose the daily level of carbon monoxide in the air can be modeled by the function C of P equals the square root of 0.5 P squared plus 17. This will tell us in parts per million when the population is 1,000. So if we know how many thousand people, we'll get how many carbon monoxide parts per million, ppms. It estimated that T years from now, the population will be this equation here. So the population at any time from now would be 3.1, and that's going to be 1,000. So at what rate will the carbon monoxide level be changing with respect to time of years right now? Okay, so if we think about it here, this is our population based on our time, and our carbon monoxide level is based off of our population. So if we want to find the time of the carbon, we got to take this function and plug it into there. So you are going to do C of P, actually C of T is going to be radical 0.5 of not p squared, but 3.1 plus 0.1 t squared plus 17. So what we want to do here is, if we want to figure out what rate this is changing, you're going to take the derivative of this, which it might be beneficial to change this to 0.5 times 3.1 plus 0.1 t squared plus 17 to the 1/2 power. And realize that you're going to have to do the chain rule a couple times. So if we go ahead, let's see if I can change my colors here. We have something to the 1/2 power. And then inside of that something, we have half of something squared. There we go. So we got chain rule inside of a chain rule. So what you're going to have to do is take the derivative of all this. Once you get an answer, then you're going to plug in 3. Okay. All right, the next problem's here. And this is one big problem, just front and back of the page. So we're going to look at the function here, and what I'm going to do is I'm going to split Desmos up here. Get Desmos going. All right, so Desmos is going to be real nice. So we got a function here with e to the, go ahead, actually I could probably just go e to the 1/20th x squared power. All right, so we get a graph that looks like a kind of a pretty flat U shape. In fact, if we zoom out, it looks like that even more. All right, so take a quick sketch of the graph. What we're going to do is now make a table of all the points between x in between 0 and 20. So basically, we're going to make a table here, which we can use this. And you just want everything after 20. So, all right, press enter a bunch of times. There we go. We can start to see. So 0's at 1, then we got like 1.5, 1.2, 1.56, and keep going 6, 11, 24, 70, 57, 48. All right, so what you want to do here is, based off these numbers here that we get, create a story problem that you could represent. And I used to always kind of joke about this story problem from back in the day. You know, think of something that starts out real low. We got 1, then we got 1, then we got, okay, got 2, now 3, now we got 6, 11, 24, 57. Okay, so now this number is increasing more and more and more and faster. And I used to say, you know, that could be like a, you know, the deadly zombie virus and escaping. These are the number of zombies we have. But I think now in 2020, we've learned to not always joke about those things. Okay, next what you're going to do is to take the derivative of this. And this one you have to do the chain rule. So just to help you out with the derivative, remember e to the x, the derivative of e to the x is e to the x. So we got e to something, which would be e to that something power, times the derivative of the something, the derivative of 1/20th x squared. All we need to do is take 2 times 1/20th would be 1/10 and drop x down a power. That's it. So now what you're going to do here to find f prime of 1, you're going to find the rate of change at 1. So you're going to take 1 and plug it in, and 5 and 10, plug it all into those to evaluate. All right, so then based on your story problem, what do those numbers represent? So depending on how you set up your story problem here, the derivatives will represent the rate of change of that. So make sure you're descriptive. If you're talking about like, this is the number of people infected total every day, or, you know, number of total infections per day, the derivative would be the rate of change of infection, or how many new people got infected per day. And so go through something like that. All right, guys, if you have any questions, let me know, reach out. But if not, I will see you guys next, and we'll start reviewing for the quiz coming up. You guys have a great day, and I will see you next time.